right, so now as to performance, there's various tests. Monochromatically, we've gotten to 3.5 times 10 to the minus 10 over 3 times 10 lambda over d. You can see this blue dark hole here. It's totally dark outside here, not because it works better, but because we have a field stop out there. And then with 10% bandwidth, we've gotten to about 10 to the minus 9. Officially, it's 1.6 times 10 to the minus 9. And so ultimately, for Habitable Worlds Observatory, we'd like to get to 10 to the minus 10 for 20% bandwidth. None of our official milestones are at this level yet because even the chamber can't do that. But so far, we're making progress in that direction. You can see what happens versus bandwidth here. The leakage increases. If you've got a phase error in the half-wave plate, it gets worse and worse as you get off center, and so the leakage degrades. But even with 10% bandwidth, you're almost at 10 to the minus 9, and down here, you're actually this is way down here. Our monochromatic point is not here, it's way down here somewhere. All right, and we're currently limited by little off-center defects. Oh, I'm glad I put that thing in red there to remind me. Things like this. Oh, wow, okay. So they have defects, you can ask about them later. We have off-axis segmented pupil results of 4.7 times 10 to the minus 9. So we've got an error budget, which I never planned on going into in detail here, so I'll just skip through that. But I mentioned the main limitations of the defects and the phase accuracy of the layer themselves. So we're aiming at mask uniformity. And so to summarize the vortex work, we're getting there, but the tolerances are very tight. The beam engineering actually has an SBIR award to improve their techniques. There's lots of other things to look into, such as scalar vortices, the appetizers that might be needed, and combining functions with Zernike wavefront sensing, for example. All right, but if you want to have an even higher yield for habitable worlds, we need to go to smaller inner working angles. And I have to thank someone who gave a chart very similar to this, but the imaging targets, for example, are down here at larger separations. If we can get down to this region, there's a whole other batch of targets we can be doing, such as around M stars. I'll skip the spectrum since we've seen that. There's a way to do this to get to smaller inner working angles using interferometry. Then apply it. If you want to work at less than lambda over d, you have to do single mode operations. So we're talking about optical fibers. And to reject starlight there, it's very easy. You just need an asymmetric spatial mode. And I'll show that. Actually, the previous one was bigger. So if you put a pi phase shift in between two subapertures, you actually get a negative fringe across the center where the field actually goes through 0. So it's positive here and negative here, and it goes through 0. So it can't couple into the symmetric fiber mode. And we've actually done that at Palomar, but I'll skip that. And this is just a theory. You can do this in Cartesian coordinates, so in XY coordinates, or in radial azimuthal coordinates. So you can use an optical vortex as your phase shifter in the pupil plane, and then all you have to do is focus it into a fiber. We've carried out a study for the optimal phase distribution, since there were obviously 2 choices in the previous slide. There's a lot more choices here. We actually found the optimal to be a phase knife, shown here, just 0 and pi across the whole aperture. And that gives you what could we use this for? So we made some null depth estimates for various charges, and you can see the null depth versus wavelength here. And it actually gets pretty good in the near infrared down here. The visible is not so great, so I'm not going to sell that. And we've got equations for these formulas, but remember this near infrared region, 1 to 2 microns for one chart. And you can see it's got interesting spectral features, 1 to 2 microns. And remember that null depth of 10 to the minus 6 to 10 to the minus 8, that puts us right here. So it is conceivable that if you add a little bit of instrumentation to habitable worlds, you can actually get to these targets. I think I got one more chart. Yes, this is the last one. This is to keep you from being scared, because the word nulling is sort of frightening. It used to be this big optical system. So this is not the kind of nuller that we used to work on 20 years ago and the kind that Mark used to work on. This is a phase mask in the pupil plane, and then you put in a fold mirror to go into a fiber. So you take your normal coronagraph, just add those 2 things basically, and you've got a nuller, which gets you to smaller inner working angle. I can stop there. See if there's any questions.
Yeah.
Thank you. So
we have a form by refrigerants form, which you didn't really talk about because it has a very high aspect ratio. What sort of thicknesses and spacing do you have on that?
Sort of 10 to 1.
10 to 1, and what's the spacing?
Sub-wavelength, so
Sub-wavelength.
yeah, sub-wavelength, yeah, so
half a micron.
It's a naive question, but is the phase mask wavelength dependent? And if yes, what is the limitation?
yes and no. The geometric part of it is not wavelength dependent because the axes, but you have to get the half wave condition met.
Yeah.
And for vortices, there actually are solutions due to Poncharatnam in the 50s, actually, that are very broadband. So this is actually a very good point. You can make a very broadband vortex, but you're still going to be limited by the wavefront control to about 20% bandwidth. But in principle, you can make a vortex and a quarter wave plate that are, the whole optical region.
You made some comment when you were talking about vortexes, formats, where you said you're limited by the test bed. So what do you think is limiting you right now in terms of the contrast that you use?
Oh, thanks. I can go back.
I was like,
Sorry.
I know we examined it.
Well, the main.
Slide, you can up arrow.
Oh, okay. Yeah, the main thing, I don't know if I actually need to go back. There's limitations. Yeah, there's a whole error budget here. There's a central defect, which we can cover. Then you have the phase accuracy of the layers. But more than that is these little defects. There's they have to sort of take their device out at certain points and then put it back in the chamber as they're making it. So you can pick up dust particles in between the layers. And liquid crystals are not the best thing in the world to work with because although they work obviously very well on all these screens and everything, but if you want everything to work perfectly, they sometimes have little crystallization centers and things like that within the layers.
So it's impurities in the liquid crystal. Do you think
Well,
are your
we don't know for sure. It's either in the layer or it's little dust particles. And so they're going through a whole upgrade at the moment on their SBIR program to get everything to stay in the chamber while they're making the device. And hopefully this will eliminate a lot of that. And they also add, I think they're called surfactants to make things not congeal too quickly. But yeah, first main thing is the defects right now, and then the phase accuracy, you have to get to 180 degrees over the whole bandwidth. And then there's a lot of chamber issues, and what's the other one? Even the quantization error on the deformable mirror starts to come in at the 10⁻⁻10 level.
Okay, so Eugene, another hand.